Hi, this is Raja from Kanka Labs, and today we'll talk a little bit about dBs or decibels. And if you're one of those who have ever wondered why is there something like a -3 dB point, for example, when it's about frequency responses, so doesn't it look a little bit arbitrary why they choose -3 dB? So there must be a reason behind that. Well, sometimes you find -1 dB limits for frequency responses. Why is that? It's not only a nice little round number. There must be a reason why sometimes you find -1 dB limits. And if you've ever wondered why you sometimes find as the definition of the decibel 10 times the logarithm to the base 10 of something, and sometimes you find 20 times the logarithm of something. So how can it be that there are two different definitions? What's the reason for that? And if you have ever wondered why there's sometimes an extra letter behind the dB, like an M or dBA or dBV or whatever, if you cannot answer one of these questions, then this tutorial is for you, and we'll take quite a different approach to the usual textbook-like explanation, so that in the end I'm quite sure that you will better make use of dBs and more or less fully understand what dBs is about. So let's start with the word decibel. That's quite interesting. So, okay, dB is of course the abbreviation of decibel, but we should better write it this way, because the dB, the decibel, is not the base unit. The base unit is the bell, named after famous inventor and entrepreneur Alexander Graham Bell, known for invention of the telephone, or better say marketing of the telephone. And the bell is defined as the logarithm to the base 10, not the natural logarithm, of a ratio of two powers, P1 and P2. So that is how the bell is really defined. And now two things already become clear. Well, the decibel is just as in decimeter or deciliter, it's 1/10 of a bell. So to get from bell to decibel, we just have to multiply it by 10. So that's where the factor 10 in front of the logarithm comes from. And then we have this strange ratio of two powers. So we could call P2, what's in the denominator, as the reference value. So you always compare one value to a reference value. And now, usually in electronics, you don't measure power, so you usually have your multimeter, and what you measure is voltage or current. And now let's think for a minute about Ohm's law of power. Well, what's the definition of power? Power is voltage times current. And please excuse me, we in Germany here use always a capital U for voltage, for just not to confuse it with the units of volt. So in the US or other countries you might write this as P equals V times I, but here it's U times I. Now we have Ohm's law, and we can replace either the U with an expression from Ohm's law or the I. So let's do what I always call Ohm's law of power. Let's replace the U with R times E, and we get R times I squared. And if you make it the other way around, we replace the current by just doing some math with Ohm's law, you get I equals U divided by R, and then we get U squared divided by R. Aha, okay. Now let's put this into this basic definition of the bell or the decibel. Okay, we had our decibel, and I still write it this way so that you always remember it's 1/10 of a bell is 10 times the logarithm to the base 10. That's on your calculator. You usually have two keys for logarithm. The logarithm to the base 10 usually is called log, just like as in here. And don't confuse this with the natural logarithm to the base e, to Euler's constant. That is usually designed as ln. So it's quite easy to remember. Log is, as you write it down, it's the same as the log key on your calculator. And now we replace, remember, the ratio of two powers. We simply replace the powers with our other definition, that power could also be written as the resistance times the current squared, or the voltage squared divided by the resistance, and see what we get. So we get our voltage U1 squared divided by R, and that is divided by U2 squared. So first you can see the R cancels out, and we get 10 times log 10 U1, and we get this. So it's simply the logarithm of the ratio of the voltages squared. And now if you remember from school what you can do with logarithm, if you have here an exponent, you just take this exponent as a factor in front of the logarithm, and then we get 2 times 10 times the logarithm of our ratio of voltages. Aha! So when we measure voltages, as we usually do with our multimeter, then here, that's the difference. If we directly measure and compare powers, then we have to use 10 times the logarithm of the ratio of the powers. But because we usually measure voltages, this translates simply to this factor of 20. The factor of 2 comes from the square, and the factor of 10 comes from, because we are using decibels. So that's the difference, and in most cases in electronics you're dealing with voltages or currents, and we could do the same by replacing the power with the expression here, R times I squared, and again the resistance will cancel out and we have exactly the same. So no matter if we measure voltage or current, then we have to use 20 times the log 10, log to the base 10 of our ratio. And usually what's in the denominator, our reference value, that is quite arbitrary. It's not defined to anything. Usually when you measure frequency responses, let's say in audio amplifiers, you take, for example, the level, the voltage at 1 kilohertz as a reference, and you relate all this to the measured value at 1 kilohertz. In other measurement situation, you take, well, whatever value as a reference, but it's always a ratio. It's always related to an arbitrary chosen reference value, no matter if power, voltage, or current. Just the formula differs by a factor of 2 if you use power, which you usually don't measure directly, or you take your multimeter and measure voltage or current. So the first thing I think has become clear, the difference between when using 10 times the log and when using 20 times the log. So, but the next enigma or mystery is, why is this minus 3 dB point usually defined, or a minus 1 dB point defined when it comes to the limits of frequency response? So I'm sure you have seen graphs like this, where the frequency response, as I said, for example, for an audio amplifier is shown. And I've already drawn in our reference point, usually taken at 1 kilohertz for audio measurement. And this is simply set at 0 dB. So you might measure here, let's say, a voltage of 2.357 volts, but the absolute value doesn't matter. You just simply reference all other values to this value that you choose at your reference point, which is also arbitrarily chosen, but usually in audio it's 1 kilohertz. So, and now the frequency response is either defined as the limits where the deviation from your reference is either minus 1 dB or where it's minus 3 dB, which would be here. The minus 3 dB would be here in this graph just by chance between 20 Hertz and 20 kilohertz, but the minus 1 dB point would be at some other frequency, let's say, whatever, 100 Hertz and let's say, don't know, 10 kilohertz. So, but the question is, why do you so often find minus 3 dB and or minus 1 dB? So there must be a reason for especially these two values. And so we take a look at the relative deviation in, let's call it in percent or in a factor from 0 dB, what relates to minus 1 dB and minus 3 dB. So let's make a little table with a sum of the values like 0 dB plus or minus 1, 3 dB, 10, 20, etc. And for that, let's compare the power ratio and the voltage and current ratio. So I've already written down the kind of reverse formula. So that's the inverse of the definition, just if you want to get from a dB value, again, back to the power ratio or voltage or current ratio. So you have to, first of all, divide your dB value either by 10 or by 20, depending on what you later want to have. If you want to have the power ratio, divide the dB value by 10. If you want the voltage or current ratio, divide it by 20. And then with a calculator, you just have the inverse function, which is usually, I don't know if you can see it here, it's usually with a shift log that's most often found. So that's just the inverse of the logarithm to the base 10. That's the key you have to push, 10 to the x power. And so of course for 0 dB we get here a 0 in the exponent, and that we already know that. Of course 0 dB means we are exactly at our reference point, and the ratio to our reference point is 1 or 100%. We have 100% level. Let's take back a look at our frequency response. Wherever our graph or our curve is at a 0 dB point, we have the same level as in our arbitrarily chosen reference value. So now next, let's take the first enigma. What do we get if we put minus 3 dB into this formula? And let's start here with the voltage and current ratio. And by the way, we will see that it doesn't matter so much if you take plus or minus 3 dB. Let's take minus 3 dB. I hope you can read it. We divide it by 20 and then raise it to the 10th power, and we get a voltage ratio of 0.708. Well, haven't you seen this number somewhere else? That's the square root of 2. We're coming nearer to solving this riddle. If we want to know the factor of plus 3 dB, we divide 3 by 20 and then again raise it, and we get 1.41 and etc. And that's exactly the square root of 2. So the first, so plus and minus 3 dB, they differ only by being the reciprocal. So a minus value is always smaller than 1. Here we've had, for example, here our minus 3 dB value, and the level is smaller than our reference value. If we would have a deviation of plus 3 dB, then we would have something like this, and the value would be higher. So that's easy to remember. Positive dB values are always greater than the reference value. Negative values are smaller. And the sign, just you only have, if you ever forget the sign, you just have to take the reciprocal and you can change from minus to the plus value. So, and now let's do the same for our power ratio. So we have to divide, let's start again with minus 3 dB, divided this times by 10, and we get exact or nearly exactly 0.5. So minus 3 dB is where the power goes down by a factor of a half. And of course the other way around we will get a factor of 2, but let's do it just for an exercise. So we'll take plus 3 dB divided by 10 and 10th power, and we get nearly exactly 1.995, so we can round this to a factor of 2. That's why minus 3 dB is chosen for frequency responses, because the power at the minus 3 dB point goes down by a factor of 2, or is raised by a factor of 2 if the curve would be bending upwards. But usually you have frequency responses where at the limit of your frequency response, of course, the level goes down. So that's the reason why this minus 3 dB is not an arbitrarily chosen value. It just is where the power goes down by a factor of 2. But remember, when you measure with your oscilloscope or your multimeter, you measure the voltage, and the voltage goes only down. We could write it down here by minus, 29.2%, or just when we round it, where the level, the voltage, goes down by minus 30% compared to your reference level. Or if you have plus 3 dB, where it goes up 40 or 41%. So I think that has become clear. Minus 3 dB is not arbitrarily chosen. It's where power goes down by a factor of 2. And voltage goes down by 30% to 0.708 of its initial or reference value. Now let's take a look at what's so special about the minus 1 dB point. Of course, you will know in let's say a hi-fi amplifier, minus 3 dB would be, well, non-tolerable. What you want to have is the frequency response or the limits of your amplifier or whatever your record player where you can't hear any difference. Minus 3 dB would be, of course, be audible as being less loud than the same tone at 0 dB. But the human ear can, as the minimum difference, can differ only a value of minus 1 dB. So that's quite handy for audio applications. And if we do the math, let's see what we get as the power ratio and the voltage ratio. So let's start again with the voltage ratio. So minus 1 dB, we have to divide by 20, then again take it to the 10th power, and we get a factor. Let's draw a line so that we don't confuse the different values. We get a factor of 0.89, and that is 11% in voltage drop. And so that's easy to remember. Minus 1 dB is nearly a 10% drop in voltage. It's of course different for power. Let's do it again with the formula for power. So the power goes down to 79% or minus 21%. But as we already said, we usually don't measure power, we measure voltages. And the other way around, plus 1 dB, just for an exercise, is a factor of 1.12 or plus 12%. So you can see here at the minus 3 dB we still had between the minus and the plus, if we take it in percentage, there's still a substantial difference. But if we go to smaller values, the difference in percentage is nearly the same, and we can round both values to 10%. And that's also easily observable on your oscilloscope and easily measurable just by eyesight. A 10% drop in level gives you minus 1 dB. And so that's the more stringent definition for a good frequency response. And as an exercise, you should also do for ultra high precision measurement, test and measurement equipment. They can be as accurate as plus minus 0.1 dB, and that would be in level just 1% plus or minus, so a frequency response. And that becomes already different to see at an oscilloscope screen, no matter if analog or a digital storage oscilloscope. So you need even specialized measurement equipment to measure this small deviation. So if your home built equipment or your consumer electronics is good to minus 1 dB when it comes to frequency response, you just have to observe, is it within 10% of the measured voltage or current level, and then everything is okay. If you go to the highest demand and want a flat frequency response of plus minus 0.1 dB, you already need specialized and very high quality test measurement just to measure this. Okay, and finally, what's also easy to remember, a 10 dB plus or minus drop or increase is, of course, we get here 10 to the power of 1 is just a factor of 10 in power, and the voltage and current ratio is always the square root of this. So it's the square root of 10, and this gives a factor of 3.16. And what you also often find is 20 dBs, and we know from the power ratio that would be 10 raised to the exponent of 2, and we get a factor of 100. And again, the voltage and current ratio is the square root. The square root of 100 is simply 10. So if you just remember these values, then you probably will have in 90% of your measurement situations, you'll know by experience just how level translates to dBs. 0 dB is your reference level, 100%. Plus or minus 3 dB is between 30 and 40% off from your reference level, depending on if it goes down or if it goes up. 1 dB is, if you round it, is a 10% increase or decrease from your reference level. 0.1 dB is 1%. Plus or minus 10 dB is a factor of 3.16, either up or down. And plus minus 20 dB is a factor of 10 in level. And because you just usually don't have to do with the power ratios, simply because you don't measure them, you can most often forget. But now you know where this 20 is coming from. It's the combination of the decibel in bell, and because voltage and current are squared when you want to get to power. So, and there's another field where some strange value quite often appears. I'm quite sure that you already have seen this. Minus 6 dB per, how is it pronounced? Octave, or minus 20 dB per decade. And now you can already guess where this comes from. If we do the math again, minus 6 dB is a drop in level by a factor of 2. And minus 20 dB is a drop or an increase by a factor of 10 in level. So the level ratio of voltage or current to your reference level. Now an octave is a factor of 2 times 2, or depending on how you look about it, in frequency. And the same is a frequency decade. This is a factor of 10 times 10 or divided by 10, depending on which end you look at. And that is the same. So minus 6 dB per octave is the same as minus 20 dB per frequency decade. And where do you find this? Usually in filter responses, no matter if active or passive filters. Let's say you have a low-pass filter, and here you have the roll-off, and here your filter goes down. But the axes are usually scale logarithmically. So let's say here you have 10 Hertz, 100 Hertz, 1 kilohertz, 10 kilohertz. A logarithmically scaled axis means the same distance in centimeters is always the same factor. Here we have, let's say, 3 or 4 centimeters per frequency decade. And because the y-axis is in dB, it's also scaled logarithmically. Let's say here we have our arbitrarily chosen reference point 0 dB. And now let's see here where the roll-off starts, we have, let's say, 300 Hertz. And here we would have 3 kilohertz. So that is 1 decade difference. And here, for example, we could find minus 20 dB. So in one frequency decade from 300 Hz to 3 kHz, we have 20 dB level fall off, and that is a filter that is linearly falling off, a low-pass filter with a linear fall off, because for the same amount of frequency increase as a factor, we have the same factor as drop in level. Factor of 10 frequency increase, factor of 10 going down in level. And that's why when you ever see one of these values which are identical, minus 6 dB per octave or minus 20 dB per decade, you know you have a linearly falling filter. But don't confuse this. You could also have a filter that is much steeper. The first filter here would have minus 20 dB per decade. The steeper filter, the second one, could have minus 40 dB per decade. So in a logarithmic diagram, both curves look linear, but only the minus 20 dB per decade is falling off linearly, also if you would scale the diagram in both axes linearly. The frequency scale linear, and here not a dB value, which is in itself a logarithmic value, but the measured level of voltage. So we have still one last thing, and that is that you sometimes have an extra letter behind the dB. So until now we had all our dB values because they were the ratio of two values, power, voltage or current, to an arbitrarily chosen reference level. But sometimes you want to relate your values to an absolute value. For example, you set your reference level fixed at 1 volts. And then this is what dB volts means. It's 20 times the logarithm now of your measured voltage referenced to 1 volt fixed. And so if you read something of a value in dB with a capital V, you can again reverse the formula to get the absolute value, because you know that your dBV value is referenced exactly to 1 volt. And not any arbitrarily chosen reference. Or in other words, the denominator of your ratio becomes now a fixed value. And the most common used dB values with an extra letters are, except for the dBV for dB volts, you could have a little m, and there the reference is reference to 1 milliwatt of power. Now here you have to look out. dBV values are always voltage ratios, so you have to use this formula. And you have to watch out, dBm values are referenced to 1 milliwatts, so you have to do a little bit of math, because you first have to convert your voltage to a power, and therefore you need also, of course, a defined resistance. This can be 50 ohms when it comes to radio frequency measurements. It can also be 600 ohms. So in the radio frequency range, it's usually 50 ohms as a reference, but you have to give this value. In audio measurements, it's quite often 600 ohms for audio measurements. And so if you first measure your voltage, you have to convert your voltage with the help of your defined resistance to a power and then put it into this formula. So that's a little bit complicated. dB volts was easy. You measure voltage and you put the voltage value from your multimeter into the formula. Quite simple. When you want to get a dBm value, you measure voltage or current, convert it to a power, then put it in relation to 1 milliwatts, and then take the logarithm, then take times 10, and not times 20, and you get your dBm value. So this is probably the most error-prone value if you're really using it. What again becomes more simple, just as dB with a capital W is of course referenced to 1 watt. That could be, for example, for audio power amplifiers or also radio frequency amplifiers. Then we have the dB microvolt. There it's just as in volts, referenced to not 1 volt, but of course 1 microvolt. And when it comes to digital audio, for example, you know that you have to avoid any signal that goes behind the highest digital value, and that is called full scale. It can also be analog full scale. So this is reference to your full scale value. And what else do we have? Perhaps the last and most different is dBA, and that is for loudness measurements, where you have to have a special frequency filter in front of your microphone with a special characteristic. So dBA the A has nothing to do with a reference value. It's just a filter response of a special filter that imitates part of how humans are hearing in different frequency ranges. So this is quite different from these, but I think you most often encounter dB volts, dBm as milliwatts, dB microvolts and dB full scale, and that covers, I think, 95%, plus of course the dBA for loudness measurements. So that was it for today. Basically, I only wanted to explain, because I need it in a future video, why is there especially this -3 dB. And now we know it's where the power drops to half of its reference value and the voltage or current dropped to 1 divided by the square root of 2, or 0.7 of the reference voltage, because in a forthcoming video there is another enigma about this -3 dB when it comes to impedances. A very interesting thing that puzzled me for quite some time when I started in electronics. There was something I really didn't understand, even after I understood what is -3 dB, but that will become the content of a future video about impedances. So, thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.